What does a solar cell and a glow-in-the-dark ball have in common? In this video, we will be exploring electronic spectroscopy and photophysics, which is the science of how electrons contained in molecules and atoms make transitions by absorbing or emitting light. But first, we should discuss some fundamental aspects of quantum mechanics that underlie this field of study. Quantum mechanics can be seen as the study of the transition between discrete states of a microscopic system. These states are denoted by kets. As we will see later in the video, the fundamental state that we are interested in is the spin of an electron, or its intrinsic angular momentum. This spin can be either up or down. Next, we consider the simplest possible system to explore these photophysical phenomena: a hydrogen atom, with a nucleus represented by the red circle, and an electron by the blue ring. When an electron impinges on the hydrogen atom, if it has an energy that exceeds the gap between these energy levels, the electron will be excited to the higher lying state. Next, we consider a system with 2 electrons instead of 1. We will denote the ground state and excited state more abstractly with horizontal bars, and populate the ground state with a spin up and spin down electron. The total spin of the system, denoted by S, can be calculated by summing the spins of the individual electrons. Each possible value is given a name. For 1, it is a singlet, and 3, as we will see later, is a triplet. When a photon impinges on the system as before, we can see that one of the electrons is excited to the excited state. Next, we consider the question, what transitions are allowed? This is the field of selection rules in spectroscopy. Consider an initial state I that we have mapped with the dipole moment operator denoted by mu to the excited state F. This quantity in brackets tells us the overlap between these states. After taking the magnitude and squaring it, since generally it can be complex, we obtain the probability that the system transitions from the initial to the final state. Now, let's use this tool to see if the following transition is allowed. We start with a singlet ground state, as before, and excited, but this time there's a spin flip. This changes the spin of the second electron and creates a triplet state. Next, to evaluate the selection rule for this transition, we will write the initial and final states of the system as a product of the spin part and the electronics part, denoted by EI and EF. For reasons beyond the scope of this video, the spin part must be anti-symmetrized. That is, its sign must flip when 1 and 2 are exchanged. We can now substitute the initial and final state into the expression for probability. We get a large expression that simplifies when we consider the property of orthogonality. That is, the overlap between a spin up and spin down state is 0. This means that the overall overlap simplifies to 0, that the probability is now 0, which means that this transition is forbidden. Now that we understand transitions in 2 electron systems and the rules that govern them, we will explore the physically relevant phenomena of fluorescence and phosphorescence. Fluorescence is a rapid process where materials absorb photons from their environment and re-emit this energy as light. Consider a 2-electron system moments after being struck by a photon, with an initial configuration of a singlet and an electron in the excited state. When this electron falls to the ground state without flipping its spin, the molecule emits a photon. Using similar methods to before, we can derive selection rules that tell us that fluorescence processes are allowed and are therefore fast as they are likely. Phosphorescence is a very similar process, but with a long-lived excited state that yields glows that can last minutes or even hours, as in glow-in-the-dark materials. Consider another 2-electron system, but this time with the excited electron facing the same direction as the ground state electron. This yields an initial spin of a triplet. When the excited state electron relaxes, a photon is emitted and the total spin changes to a singlet. As we derived before, this is not an allowed transition. This means that phosphorescence is slow and spin forbidden.